What's up, guys? Welcome to Calculus Club. In this video, we are going to get into the derivative. So the derivative is a very big concept within calculus, okay? In this particular video, we're going to talk about the limit definition of the derivative and the tangent line, all right? So we're going to be specifically concerned with how to find the slope of the tangent line, okay? And spoiler alert, the slope of the tangent line is the derivative, okay? Let's get into it. So imagine, so what is a tangent line, okay? So if I have a circle, the tangent line at the point P is gonna be the line that is perpendicular to the radius, also called the radial line, that passes through P. So here, perpendicular, remember, is 90 degrees. So this 90-degree line to the radius is tangent to the circle, okay? If it's tangent to the circle, it means it touches at just one point. So if I were to zoom in at that point P, get closer and closer, you would see that actually this line only touches at one point, okay? All right, so let me just show you a few graphs of different tangent lines, okay? So we have here is a graph of a tangent line. It only touches at that point P, all right? Here's another example of a tangent line, and it only touches at P. It would touch again down here, but we're not concerned with that. We're just zooming in on P, okay? Here's another example where if you zoom in on P, it would only touch at one point. And this one's a little interesting because it actually crosses the line, but that's okay. And the main thing here is that this tangent line would represent the instantaneous rate of change of that function, okay? So for example, if I look here, the instantaneous rate of change is just, well, rate of change just means slope, if you remember that from algebra, okay? So the instantaneous rate of change is the slope at that instant at that point P, okay? So if we take a look at this one, and I think the best way to think about this is think about a plane flying along the tangent line, okay? Is that plane ascending or descending at that point P, and at what rate is it ascending, is it descending? So you can see here at that point P, well, the plane would just be flying in a straight line, right? So it would neither be ascending nor descending, and you probably already remember that this slope is zero, right? Because the slope, remember, is like change in y over change in x. And on this one, if x changes anything, if x changes 1, the y changes 0, right? So that slope is 0. So the derivative, or the instantaneous rate of change of the tangent line, is 0, okay? If we look at this one, all right, well, now that that plane is descending, okay, and let's just make it very easy. Let's say that this is like 1 and this is 1. Or we can put -1 if you want, but the idea here is that if the x changes 1, the y would change -1, okay? So the plane would descend maybe 1 meter vertically for 1 meter horizontally. So we say the slope, or the derivative, or the instantaneous rate of change is -1, okay? This last one, it's going up 1, so we can say that it is about positive 1 for this last one, okay? And that is what the derivative is doing. You're finding the instantaneous rate of change, okay? The slope. So let's talk a little bit now about how we mathematically come up with calculating this derivative, okay? So what we're gonna do is we're gonna be talking about a secant line here, okay? So if you remember, let's say that what we're gonna do is we're gonna try to calculate the slope of the tangent line, or the derivative, at this gray point, all right? And the way that we're gonna do this is we're going to first take a secant line. So a secant line is this blue line. Like, let's say I extended it, okay, and this line here. This is the secant line. It passes through 2 points. The tangent line passes through 1. secant line passes through 2, okay? So, all right, so I'll take this out. So I stopped with the secant line passes through 2. All right, so the idea here is that we're going to take this black line, this black point, and we're going to move it closer and closer to the gray. All right. So we do it here. So you see now we've moved the black along the line a little bit, and now we have a new secant line, this new blue line. And then we would do it again, and we would allow this black line to get closer to the gray. And the idea is as this black line gets really close to the gray, then you would actually get the slope of the tangent line. All right, let me show you this. All right, so here you have P and Q. So P is like the gray point, Q is like the black point. And the idea here is I have this secant line, okay? And what I'm gonna do is I'm gonna allow this green to become closer to the P, to the blue, and notice as that Q gets closer and closer, this secant line is becoming closer and closer to that tangent line, okay? So this is the idea here when we will come up with the equation for the derivative using a limit, all right? So before I develop the limit definition of the derivative, let me just remind you of something really quick. So let's say that this blue line is the line f of x. Okay, so if this is, for example, like 2, then this point on the blue line is going to be f of 2, okay? Which means this y value is f of 2, right? I'm sorry, the y value of that point on the line will be f of 2. And if this is, I don't know, let's say that this is 5, right? Then this y value here on the line will be f of 5. Okay, so to develop this, instead of 2, we'll have x. Okay, so if I replace this 2, if this is just the value x, then this point would just be f of x. That f function evaluated at x. This one is going to be x plus delta x. And I'll explain all this in just a second. Okay, which means this value is now f of x plus delta x. Okay, so this y value is f of x plus delta x, just that f of x evaluated at this x value, which is x plus delta x. Okay, hope that made sense. Now let's get into the limit definition of the derivative. Okay, so let me show you what we're going to do here. So first of all, we're going to take a secant line, so we're going to pass through this point. Now I'm going to call this point x, which means this y value I'll just call f of x. And then I'm going to call this point, okay? So I'm going to let this distance here between x, I'm going to let this distance be delta x, okay? The distance from this point x to this new point is delta x. So the x is going to be x plus delta x, right? Because from here to here is x, from here to here is delta x. So from 0 all the way to this will be x plus delta x. And the y value here will be f of x plus delta x on that, okay? So I can define these points. So this point here is x, f of x. And this point is going to be, my x value here is x plus delta x. And the y value is f of x plus delta x. Okay, so now let me come up with the an equation for the slope of the secant line. Okay, so the slope of the secant line, let me draw it here. Okay, so we'll call this change in y, and we've already called this change in x, but I'll write it again. So the slope of the secant, right, and we often call the slope an m. So we'll put m of the secant is gonna be the, that should say secant. Need to work on my handwriting. I will rewrite that because that's pretty, let's just call it SEC, which means secant. So the slope of the secant, first of all, is change in y over change in x. All right. Now, because we have our y values, we can get our change in y. If you remember, y2 minus y1 over x2 minus x1, right? So this is like x1, y1. And this would be like our x2, y2. Sorry, that should be a comma, not a parentheses. X2, y2. So our y2 minus y1 is f of x plus delta x, minus our y1, which is f of x, over x2 minus x1, which is x. And we already knew that that's delta x, but I just wanted to show you all the parts. So these are going to cross out. You're going to be left with the slope of the secant is f of x plus delta x minus f of x over delta x. Okay? And now, what are we going to do? Well, we're going to allow this point here. Okay, let's change colors. So what we're going to do is we're going to allow this point to move along the line until it gets to the red point, okay? So another way to think about this is we're gonna let this delta x get smaller and smaller and smaller. So what we're actually doing here is we are taking the slope of the secant, the limit as delta x approaches 0 of the slope of that secant line. Okay, so I'm going to make some room here. So what is the slope of the secant line? Well, we just found the slope of the secant line to be this. So what we're doing is we're taking the limit as delta x approaches 0 of the slope of that secant, which is f of x plus delta x minus f of x over delta x, okay? And if you calculate this limit, you will get the derivative, okay? So I'm going to do this in a couple problems, but this is the important thing. And in most calculus classes, you're going to need to be able to come up with this equation, all right? And yeah, so that's the equation there. So to show you everything, we're taking the limit as delta x approaches 0 of the slope of the secant, which is the change in y over change in x. And this is the equation as I just showed you how to come up with it. All right. And this equals f prime of x. So f prime of x means the derivative of f at x. Okay. This is how you will always refer to the derivative with this f prime. Okay. One other thing I want to mention to you. So first of all, this is the slope of the tangent line at any point x, f of x. Sometimes you will get f prime of x as a new function of x, okay? And we'll do all this, we'll do all that right now. So the one other thing that I want to mention to you is a lot of times you'll see this written with an h instead of a delta x. So if I replace all of these delta x's with h, all right, I get this. These are equivalent. These are just two different ways of writing these, okay? All right, so let's get into an example. Let's say I want to find the derivative f prime of x of this function 2x minus 3. So the first thing I'm going to do, let's come up with the equation. The equation is take the limit as delta x or h approaches 0. I'm going to stick with the delta x. So the limit is delta x approaches 0 of f of x plus delta x minus f of x over delta x. And you want to have that memorized, okay? So now let's determine these. Well, let's find f of x plus delta x. F of x plus delta x. Well, I'm just going to plug in x plus delta x for that x. So it's going to be 2x plus delta x minus 3, which I can write this as 2x plus 2 delta x minus 3, okay? Our f of x is just 2x minus 3, all right? So let me write this all now, and I'll change colors here so we keep it straight. So now we're going to take the limit as delta x approaches 0 of f of x plus delta x, which is 2x, plus 2 delta x minus 3, minus f of x, which is 2x minus 3, divided by delta x. All right, so what's going to happen is a lot of things are going to cross out here. So first of all, this is positive 2x. This will be a negative 2x when I distribute that negative 2x. And the negative 3, negative 3 will actually be a positive 3, so these will cross out. So now I'm left with the limit as delta x approaches 0 of 2 delta x over delta x, because everything else is crossed out. Well, these delta x crosses out, so I'm left with just the limit as delta x approaches 0 of 2. 2 is just a constant. The limit as delta x approaches 0, or the limit as x approaches 0, or the limit as h approaches 0 of 2 will always be 2. Okay? So that means the derivative f prime of x, let me change color one more time here so we keep it straight. So that means that the derivative of 2x minus 3 will always be 2. And that makes sense because think about the line 2x minus 3, right? The line 2x minus 3 is just a line, and the slope, or the derivative, the slope of the tangent line is always 2. So it makes sense that the derivative of this is always 2. All right, let's do another one. So let's say I want to find the derivative of x squared plus 1. So it might be worthwhile to try to pause the video and try to do this on your own, okay? Same thing's gonna happen. A lot of things are gonna cross out, and then you're gonna be left just with, you'll be left just with an x. Notice the delta x's will go away. The limit as delta x approaches 0 are gonna go away. You're gonna be left just with x's. So pause the video and see if you can figure that out before I show you how to do it now. All right, so I hope you paused the video and you tried that. So the first thing you want to do is go ahead and come up with the equation. So the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x. Okay, so what is f of x plus delta x going to be? All right, we're going to plug in x plus delta x for this x. So it's going to be x plus delta x squared plus 1. All right. So let's go ahead and square it. And what are you going to get? You're going to get x squared plus 2 x times delta x plus delta x squared plus 1. Okay. And now what we're going to do is we're going to go ahead and plug in f of x plus delta x to this equation, f of x into this equation, delta x, and let's see what happens. Okay. So the limit as delta x approaches 0 of f of x plus delta x, which we know is all of this. So let me use a highlighter to make this really clear. F of x plus delta x is all of this. Okay, and then the f of x, of course, is all of this, and delta x is just delta x. So let me go ahead and plug it in. F of x plus delta x, which is x squared plus 2x times delta x plus delta x squared plus 1 minus my f of x, which is x squared plus 1 divided by delta x. All right, so a lot of things are going to cross out. X squared and a negative x squared will go away. 1 and a negative 1 will go away. All right, and then also we have a delta x, and a delta x. So this delta x, one of these delta x, and this delta x will go away, and we will be left with the limit as delta x approaches 0 of 2x plus delta x. Okay. As delta x goes to 0, that goes away. So in the end, we get our answer of 2x. Okay, and that means the derivative f prime of x will always be equal to 2x. Moving along, now let's actually apply this. So let's find the slopes of the tangent lines to this graph at a couple points, all right? So we just saw that the slope, f prime of x, is 2x, which means the slope at any point x we can find using the equation 2x. So for this 0, 1, we just plug in the 0, so f prime of 0 is 2 times 0, which is just 0. All right? F prime of negative 1 is just 2 times negative 1, which is just negative 2. So what does that mean? That means if I take that the line x squared plus 1, which is this black line here, notice the tangent line at negative 1, this has a slope of negative 2, and you can see down 2 over 1, all right? And we can also see that the slope at 0 has a slope of 0, right? The tangent line at 0, or the slope of the tangent line, or the derivative at 0 equals to 0. Okay, and that's what you're doing when you're finding the derivative, is you're finding the slopes of these tangent lines. Okay, so just a couple things here. The derivative of this function, all right, is 2x, and notice that that the derivative is also a function. So I can graph, and we'll do this later where we graph the functions and their derivatives. So the graph of the derivative is also a function. That's all I want you to keep in mind, okay? And what this function allows us to do is it allows us to calculate the slope of a tangent line at any point x, f of x. We can calculate the slope of that tangent line using this derivative function that we've just found. All right, so the good news is later it's going to become easier to find the derivative. You're not going to have to do this really long process with the h or the delta x, but you need to be able to do it because this is where the derivative comes from, and because a lot of calculus teachers will test you on that. All right, so yeah, that's everything for this video. I hope this was helpful and it helps you to understand the limit definition of the derivative and where the derivative comes from. So if it was helpful, if you can also help me by giving me a like, comment, share this with your friends, all of those things really help me to reach more students. So thanks for watching, and I hope you tune in for the next one. Bye-bye.